My name's Owen Calder, and this is my Lab 4 lab report. The purpose of this lab is to experimentally determine the dipole moment of a bar magnet. We'll use our phone's magnetometer. We'll move the phone at varying distances from the magnet and observe how the magnetic field it measures changes. The system consists of the bar magnet and a meter stick, and the surroundings are uh, the lab, including any nearby electronics that could interfere, and the Earth's magnetic field. We calculated the dipole moment to be 7.1 amp meters squared, and we verified this value with a computational model in GlowScript. Some important ideas: we'll be using these equations. The B field due to a dipole on axis parallel to the dipole moment. By measuring the distance and the B field's x component at a bunch of points, we can graph those points to calculate the dipole moment mu. The second equation we will use to compute the B field in the computational model. For experiment, we moved the magnetometer along the meter stick until we reached certain B field values, 20 through 220 microtesla. Then we measured those distances and plotted the points on a line, or plotted the points on a graph. We plotted the natural log of the B field over the natural log of the distance, resulting in this graph and this equation. We also plotted a few points. We didn't plot, but we measured a few points 45 degrees from the meter stick, which we will eventually use in a computational model. For our calculations, we know that B varies with distance. So we can say B equals KR to the N, where K and N are constants. We graphed the natural log of B over the natural log of R to calculate K, which we calculated to be 1.42 times 10 to the negative 6. We know that the B field due to a parallel dipole is given by the equation from before, B equals K 2 mu over R cubed. So if we make those two equations equal, we can solve for mu and get 7.1 amp meters squared. I then created a computational model. I wrote a function given mu and r. It will calculate the B field at that observation point. And then using this function for a bunch of observation points yielded this, where the B field, as expected, comes out of the North Pole, loops around, and if we plotted points over here, it would go back into the South Pole. At this distance, this diagonal distance, 32.5 centimeters from the magnet, we measured the B field to be negative 7 microtesla in the x direction and negative 17.3 microtesla in the y direction, but adjusting for interference due to the Earth's magnetic field, that value should be 13.6 microtesla in the positive y direction. This differs significantly from the values computed by the model, but the signs and direction are the same, and they're of the same order of magnitude. What if the meter stick wasn't oriented to compensate for magnetic north? We would have to do extra calculations, subtracting the contribution of the magnetic north from our measured values. And if we stuck two identical magnets end to end and repeated the experiment, we would calculate the magnetic dipole to be around twice as large as the original. Possible sources of error in our experiment include fluctuations in the magnetometer app and interference due to electronics and the Earth's magnetic field. in conclusion, we successfully calculated the magnetic dipole moment of a bar magnet. We showed how the magnetic field due to that magnet changes with distance, and we corroborated our calculated value with the computational model. Thank you for listening.